Hey guys, it's Medicosis Perfectionalis, where medicine makes perfect sense. Today we'll talk about the Haldane effect. By the way, the Haldane effect is the exact opposite of something else called the Bohr effect. So we'll talk about them both in today's video, so let's get started. Now, patients who have COPD, who happen to be hypoxemic, which means they have hypoxemia, which is low PaO2 in the blood, which is one cause of good old hypoxia. On one hand, these patients need supplemental oxygen to mitigate their hypoxia. On the other hand, oxygen can lead to hypercapnia. This phenomenon is called oxygen-induced hypercapnia or hyperoxic hypercapnia. You should not withhold oxygen just to prevent the oxygen-induced hypercapnia. If these patients need the oxygen, they should get the oxygen. Oxygen-induced hypercapnia has three main causes. Number one, which is by far the most important, is worsening VQ mismatch. There is increased dead space. We call this dead space physiology or wasted ventilation. It's being ventilated but not perfused. This is a wasted ventilation. The second one, which is today's topic, is the Haldane effect. And the third one is hypoventilation, specifically decreased the minute ventilation. If you want to be more sophisticated, we can expand them. So worsening VQ mismatch, Haldane effect, hypoventilation, and there is the idea that when you give oxygen, oxygen is an anxiolytic, which means it destroys anxiety. It's anti-anxiety. It's also anti-dyspneic effect. So you basically tend to sleep and become kind of drowsy. This will decrease the tidal volume because when you sleep, the tidal volume goes down. When the tidal volume goes down, ventilation will go down. This will increase PaCO2, which is the same thing as saying it's a hypoventilation, but in another way. Hypoventilation can also decrease inspiratory flow demand, which will decrease the amount of room air around a face mask or a nasal cannula, which will increase FiO2, which is the percentage of oxygen in the atmosphere. This will worsen the hypercapnia. Again, 5 and 4 are basically subtypes of hypoventilation. Let's talk about hypoventilation, shall we? Yes, hypoventilation decrease minute ventilation. What is minute ventilation? Minute ventilation is the same thing as pulmonary ventilation, which is basically respiratory rate times the tidal volume. That's it. Thank you so much. But alveolar ventilation is different. Alveolar ventilation is respiratory rate times the tidal volume minus the dead space. Let's talk about hypoventilation again. Pulmonary or minute ventilation, what's going to happen to it? Since the respiratory rate will decrease, the pulmonary ventilation or the minute ventilation will also decrease. What's going to happen to the alveolar ventilation? Respiratory rate first is going to decrease. The dead space has increased. Look at this. This is wasted ventilation. When you increase the dead space, what do you think is going to happen to this entity? When you increase the dead space, this whole thing will go down. This is called math. When this decreases and this decreases, what's going to happen to the alveolar ventilation? It's going to go down. So the dead space to tidal volume ratio increased because the dead space has went up and the tidal volume has gone down, both of which will increase the ratio. VQ mismatch. Normally, this is it's like 80%. Ventilation defect, it's decreasing. Could be 0 if you take it to the extreme, but basically it's going down. We call this shunt-like physiology because it's not ventilated, but it's perfectly perfused. So the blood is kind of shunting without being ventilated. This is called a shunt-like physiology. The third story, which is today's story, the perfusion defects. You cannot perfuse this, but ventilation is happening. But this is wasted ventilation because it's being ventilated but not perfused. We call this wasted ventilation or dead space physiology. The VQ ratio has increased and the dead space has also increased. Normally, when you have hypoxia, pulmonary vasoconstriction will occur, and we call this hypoxic pulmonary vasoconstriction, not to be confused with the human papillomavirus. Haha. This will lead to redistribution of blood flow to well-ventilated areas. Basically, here's the story. This is a blood vessel, and this blood vessel is supplying a piece of lung which is bad. It's hypoxic. So we constrict this blood vessel to allow other blood vessels to perfuse normal areas of the lung, which is exactly what we want. This is called hypoxic pulmonary vasoconstriction. You constrict this one. This will improve the VQ match and decrease the physiological dead space. This is amazing. But in COPD, there is a loss of this phenomenon. You cannot perform hypoxic pulmonary vasoconstriction. This will increase the dead space, worsen the mismatch. This is called dead space physiology, which are areas that are ventilated but not perfused. This is horrible. Normally, you breathe air in. Imagine my shock. When you breathe air in, the percentage of oxygen in the atmosphere is called FiO2. Then it goes to your lung to become P big AO2, A for alveolar. Then it jumps from the lung to the pulmonary capillaries or arterial blood. This is called P small AO2. Then jumps on the hemoglobin. Oxygen jumps on the hemoglobin, becomes SaO2, the percent saturation. How much of this hemoglobin is saturated with oxygen? Then the hemoglobin will go to the tissue in order to supply the tissue with the great oxygen and take the ugly CO2. Ugly CO2 will jump on the hemoglobin. Hemoglobin is now called carbaminohemoglobin. But hemoglobin with oxygen was called what? Oxyhemoglobin. So this is oxy and this is carbamino. Or carbamino. And then it goes to the venous blood called PVO2. Then to the lung you exhale the CO2 out. Thank you so much. Please forget this garbage down here. It was from another video, but I was too lazy to delete it. Sorry. Now let's talk about Mr. CO2. CO2 is present in your blood in physical form and chemical form. Same thing with oxygen, but now we're talking about CO2. Physical form or dissolved form. This is CO2 that's dissolved in the blood. These are the bubbles, the air bubbles. When you put oxygen in a glass of water, you have oxygen in water. This is like how the fish breathe. Oxygen dissolved in the water. But when you put CO2 in water, yeah, it gets dissolved, but something horrible is going to happen. Acidosis. Woo! Why? Because you have an enzyme called carbonic anhydrase. Anhydrase will take the water out of the equation and form another compound that does not include water, which is called carbonic acid. Carbonic acid will then be dissociated into bicarbonate and the nasty acid. This was the physical form. The chemical form is either bicarbonate or carbamino compound. It depends on your location. If you are located in the red blood cell, you will have potassium bicarbonate, and this potassium bicarbonate is the one that includes the CO2. You see CO2 here within this compound? Yes. But if you are in the plasma, which means outside of the red blood cell, you are in the form of sodium bicarbonate, and the CO2 is here as you see. Why do you say potassium inside the RBC and sodium outside? Because if you remember cellular physiology, you know that potassium is more prevalent in the intracellular fluid and sodium is more prevalent in the extracellular fluid. Hello? Then, carbamino compounds. If you are within the RBC, you are carbaminohemoglobin. If you are outside of the red blood cell, you are carbaminoprotein. Why not hemoglobin outside of the RBCs? Because hemoglobin is inside the RBCs. That's where it's supposed to be. Let's talk about the Haldane effect and the Bohr's effect. When oxygen binds to hemoglobin, CO2 tends to leave the hemoglobin. This is the Haldane effect. But when CO2 binds to hemoglobin, oxygen tends to leave the hemoglobin. This is called the Bohr's effect. Some of you will say, oh, this kind of saying the same thing. You're as naive as the B lymphocyte before it recognizes the antigen. No, it's not the same thing. They are close, but they are not the same. So what's the Bohr effect? CO2 binds to hemoglobin, displaces oxygen out of the hemoglobin, which means oxygen unloading. What's the Haldane? When oxygen binds to the hemoglobin, it displaces CO2, hashtag CO2 unloading or CO2 delivery, because CO2 is leaving the hemoglobin. How do you remember medicosis? Easy. B here and C here. You remember ABC? Yes, C comes after B. So the Bohr's effect, you start with the CO2. CO2 binds to the hemoglobin, displaces oxygen from the hemoglobin. This is the Bohr. Haldane is the other one. Some students are crazy. They will form a mnemonic for this one and create a mnemonic for this one. But in the real exam, you will switch them around and you will get confused. You remember one and the other one is the other one. Thank you so much. Why is Bohr and Haldane effects crucial? I'll tell you why. Because if you are at the lung level, we would like the hemoglobin to bind oxygen and leave CO2 at the same time. Also at the tissue, we want the hemoglobin to leave the oxygen to give it to the tissue and take the CO2 at the same time. These two steps happen at the same moment, thanks to Haldane effect and Bohr's effect. But this is astonishing. Why astonishing? Because normally oxygen binds to the iron portion on the hemoglobin, and the CO2 binds in a completely different location, which is the NH2 partition in the hemoglobin. But when oxygen comes to bind to the hemoglobin, CO2 tends to leave, and the opposite is also true. Let's go back to the oxygen dissociation curve or oxygen hemoglobin dissociation curve. I've made 2 separate videos about this topic. You can check them. They are available on my channel, Medicosis Perfectionalis. So here is the percent saturation of oxygen on the hemoglobin, and here is the partial pressure of oxygen in the freaking blood. And here is shift to the right and shift to the left. Why do you shift to the right? To increase giving of oxygen to the tissue. Hashtag oxygen unloading or oxygen delivery. What shifts the curve to the right? You have increased PCO2, increased hydrogen ion concentration, increased temperature, altitude, and 2,3 BPG or DPG. Increase PCO2 will shift the curve to the right, increases oxygen unloading, and this is the Bohr's effect. Oh, bingo! Now it makes sense. In other words, when you give the hemoglobin carbon dioxide, the hemoglobin will tend to give oxygen to the tissue. So, the Bohr's effect starts with a B. Define the Bohr's effect. Start with a C. When CO2 binds the hemoglobin, oxygen tends to leave. Oxygen tends to be delivered to the tissue. Now, here is a big difference. This is the oxygen dissociation curve. This is the carbon dioxide dissociation curve. What's the difference? First, the horizontal axis is kind of the same. This is P small aO2. This is P small a CO2. Okay, like it's analogous. We get it. But here, this is the percent saturation of oxygen. This is not the saturation. This is the carbon dioxide content per 100 mLs of blood. There is another big difference between the 2 curves. This looks like an S. So, S-shaped curve in oxygen dissociation curve. Why? Thanks to the cooperativity of hemoglobin. What the flip does that mean? Here is the RBC and here is the hemoglobin. Once the first oxygen molecule binds to the hemoglobin, it gets easier. The curve gets more vertical. It gets easier to the second oxygen to come through, and it gets even easier to the third oxygen molecule to jump on the hemoglobin. That's why the curve gets like this. It gets more vertical until the hemoglobin is kind of saturated and it flattens out. But there is no cooperativity for carbon dioxide. That's why the shape of the curve is basically a straight line or kind of close. This dissolved CO2 is the CO2 that's in the blood. This is the physical form, but this CO2 is the CO2 on the hemoglobin, and this is technically the chemical form. The difference between these 2 lines is called tidal CO2. It's like a tide. When the hemoglobin goes to the lung, it gives the CO2 to the lung, so the CO2 in the blood goes like this, down, by about 4. From 52 to 48, that's about 4 mLs per deciliter. And then, after we leave the lung, we go to the tissue. And in the tissue, the CO2 gets loaded on the hemoglobin, so it goes back up towards the 52 and goes to the lung, goes to 48, to the tissue, 52, to the lung, 48. It's like a tide. That's why we call it tidal CO2. This amazing brown line here is the freaking Haldane effect. Let's talk about the Haldane effect. There is oxygen in the blood. Oxygen jumps on the hemoglobin. Then it will shift the curve to the right. What curve are you talking about? The carbon dioxide dissociation curve. If you remember the previous curve, which is the carbon dioxide dissociation curve, the first one was like this. When you shift it to the right, to the right and downwards, it becomes like this. What happened from the blue line to the red line? Basically, the red line is oxygenated blood. This is the oxyhemoglobin. So oxyhemoglobin shifts the curve to the right. You can say to the right and downwards. What's going to happen? This decreases the hemoglobin affinity to CO2. Hashtag CO2 unloading, which means there is increased CO2 in the blood. This is hypercapnia. That's why we call it oxygen-induced hypercapnia or hyperoxic hypercapnia. Amazing. oxyhemoglobin binds CO2 less avidly than the deoxyhemoglobin, which kind of makes sense because this is called oxyhemoglobin. Oxyhemoglobin should carry more oxygen and less CO2. It's like common sense to me. Oxyhemoglobin versus deoxyhemoglobin. Oxyhemoglobin binds more oxygen and less CO2. It also binds less hydrogen ion. Deoxyhemoglobin binds more CO2, yeah, it's called deoxy, and it binds more hydrogen, yeah, it's called deoxy. The only thing unique about deoxyhemoglobin is that it carries more oxygen. That's why we call it oxy. How about the deoxy? It does not carry more oxygen. Instead, it carries more CO2 and more hydrogen ion. When it carries more CO2, it's called carbaminohemoglobin. When it binds more hydrogen, it becomes a beta proton acceptor. In other words, the CO2 makes the hemoglobin less acidic because if you remember chemistry, what is an acid? An acid is something that donates protons. What is a base? A base is something that accepts protons. If you accept protons, you are more alkaline and less acidic. So you can argue that when oxygen binds the hemoglobin becomes more acidic, but when carbon dioxide binds the hemoglobin, it becomes less acidic. Again, here is the difference between oxyhemoglobin and deoxyhemoglobin. When oxygen binds to the hemoglobin, it becomes oxyhemoglobin, which means it binds more oxygen, but less CO2, less hydrogen, i.e. it's more acidic. Why more acidic? Because it tends to donate more protons. Deoxyhemoglobin, when CO2 binds on the hemoglobin, it becomes a carbaminohemoglobin, binds more hydrogen and therefore becomes less acidic and more basic. Alright, fine. Now let's talk about this crucial equation or two equations, and for the next 5 minutes I would like you to do without your stupidity just for a little while. After we're done with them, you can retrieve your stupidity back, just like how the proximal convoluted tibial retrieves the bicarbonate back. Haha. Okay, here's the CO2 in the blood. CO2 will jump from the blood and on the hemoglobin. This red line here is the membrane of the glorious RBC. CO2 comes into the red blood cell, jumps on the hemoglobin, but a disaster is about to happen. CO2 plus water, thanks to carbonic anhydrase, which removes the water from the equation, gives you carbonic acid. That's a freaking acid. And then it gets dissociated into bicarbonate and hydrogen ions. That's a freaking acid. This same hydrogen ion will jump on the hemoglobin or will interact with the hemoglobin, and now this is an HHB. Do you think this is more acidic or less acidic? The answer is less acidic. Why less acidic? Because it binds the proton instead of donating a proton, so it's less acidic. This equation is reversible. You can go this way, you can go this way, you can go this way, or go this way. So let's make believe that this is a deoxyhemoglobin. All right. It will deoxy, so here it will move in this direction. It will produce more hydrogen ions or protons. Hydrogen ions will bind hemoglobin, and hemoglobin will become HHB. And this is less acidic, as you know. In other words, the direction of the reaction is going towards the red arrow. From here to here, from here to here, and from here to here. Thank you. This happens if it's a deoxyhemoglobin, which means CO2 is binding the hemoglobin. So, if it's a deoxyhemoglobin, it binds more protons, forms more HHB. Therefore, when everything here in the H becomes here an H, and you get rid of the H by forming HHB, the previous reaction will shift towards this way, to the right. The direction will be to the right to produce more protons because you are consuming all of the protons that I've produced. When you consume all of the protons, I will make more protons to make it balance. This is called Le Chatelier's principle. This previous reaction will shift to the right, to this direction, in order to produce more protons. This will lead to more CO2 entering the cell to replete the protons so that we can move in this direction and make more protons so that the hemoglobin can bind more protons and become HHB, which is less acidic. This will increase the capacity of the hemoglobin to the CO2, which is coming to bind to the hemoglobin. When you increase the capacity of hemoglobin to CO2, this is called decrease CO2 unloading or decrease CO2 delivery. Now, the opposite is going to happen with the oxyhemoglobin. If this is an oxyhemoglobin, we will reverse the direction. See the blue line? Yes, we will move in the direction of the blue line. HB will become hemoglobin plus freaking protons. And then the protons will here, we will shift to this, shift to this, shift to this, and then the CO2 will not come in the hemoglobin. Instead, we will kick the CO2 outside of the hemoglobin, and this is the freaking Haldane effect. When you add oxygen, CO2 tends to leave. This is the Haldane effect. Easy peasy, lemon squeezy, medicosis schmeezy, everything is in this equation. Amazing. Hemoglobin can bind to oxygen or protons. These two compete with each other. Hemoglobin can also bind oxygen or CO2. These two compete with each other. Here's the first equation. Hemoglobin, this is an oxyhemoglobin, plus H will give you H hemoglobin plus oxygen. The opposite is also true. Hemoglobin oxygen plus CO2 gives you hemoglobin COO, which is CO2, plus H plus O2. What's going to happen if you have more oxygen? If you have more oxygen, these reactions will tend to shift to the left. Yes. So oxygen will bind the hemoglobin to form oxyhemoglobin, and therefore hydrogen will leave the hemoglobin, and now hydrogen is free. What do we call a substance that donates protons? An acid, baby. So hemoglobin is becoming a stronger acid. What else is going to happen from the second equation? Oxygen will bind to hemoglobin. Thank you so much. This is called oxyhemoglobin, and the reaction is moving this way. CO2 will leave the hemoglobin. CO2 is now free to go to the blood. We have kicked it out of the hemoglobin. Go to hell CO2. This will lead to hypercapnia. This is the Haldane effect. If you have more CO2, on the other hand, follow the equations, but now we will use the red color. And the first one here, please look at this, not the first equation, this equation. When you have CO2, carbonic anhydrase will make it H2CO3, this is carbonic acid, and will make it into protons. Protons will bind to hemoglobin, forming HHB, which is less acidic. Now, if you go to the second equation here, when you have lots of CO2, the reaction will move in this direction, and oxygen will be kicked out, and this is called the Bohr's effect. What's the Bohr's effect? When CO2 binds to hemoglobin, oxygen tends to be kicked out of the hemoglobin. This is the Bohr. So what's the Haldane? The Haldane is when oxygen binds to the hemoglobin, CO2 tends to leave. But the Bohr's effect, when CO2 binds to the hemoglobin, oxygen tends to leave. Here is the carbon dioxide dissociation curve. CO2 content here and PaCO2 here on the horizontal. This is the dissolved CO2. Let's look at the blue line first. What's the blue line? This is the venous blood, deoxygenated blood. It has less oxygen, more carbon dioxide. This happens at the tissue because the tissue has less oxygen and more carbon dioxide. That's why the tissue gives carbon dioxide to the hemoglobin. And as you know, this is the 52 and this is the 48. The difference between them is called the tidal CO2. This brown line is the Haldane effect. Let's look at this deoxygenated blood. In the deoxygenated blood, the PO2 is 40. This is the same thing as PaO2, 40. This is less than the arterial or oxygenated blood. Okay, venous blood, PO2 is 40. What is the PaCO2? Well, it depends on the location. If you are in the tissue or in the veins, you have lots of CO2. It's basically 45 or 46. And if you go up here until you intersect with that line, and you go here, this is 52. So in a venous blood, let's say this is like a cell, and it just dumped the CO2 into or onto the vein. Now the vein has 52 ml% of CO2. Thank you so much. Now, what is the Haldane effect? The Haldane effect is this nice brown line. So let's talk about the second line. This is the oxygenated blood. PaO2 is 100. This is oxygenated, is the same thing as arterial blood. More oxygen, less CO2. This happens at the lungs. Okay, fine. Okay, lung, please talk about yourself. First, if you are an arterial blood, first before you go to the lung, let's say that this is a normal cell. And here is an artery next to the cell. The artery should give it oxygen. Okay, so the arterial blood has more oxygen, but less CO2. Less CO2, do you mean 40? Absolutely yes. Then what's going to happen to the lung? Follow the line. And then when you follow the line, you will realize that at the lung, this is 48. So at the lung, this is 48, which means the difference between the venous and the arterial side is 4. This is the oxygen that you get rid of at the levels of the lung. That's why we call it tidal CO2. This is basically the Haldane effect. Define the Haldane effect. When oxygen binds to the hemoglobin, look at the red line, CO2 tends to leave. Look at this tidal CO2. CO2 has left. We went down from 52 to 48. This delta, this 4, is CO2 leaving. Go to hell, CO2. In order for you to understand why the Haldane's effect is so crucial, let me tell you what happened before the Haldane effect. Let's say there is no Haldane effect. We only have the blue line, the deoxygenated blood. Deoxygenated blood, look at the first one, it intersected with 52. Look at the second one here, like the 40. So the 40 and the 46, or you can say 40 and 45. Okay, the delta here was only 2. What is this 2? This is the CO2 delivery. This is the CO2 being kicked out of the hemoglobin, go to hell CO2, and it gets exhaled by the lungs. The delta was only 2. But thanks to the Haldane effect, the delta became 4, not just 2. So, you might say, oh, from 2 to 4, that's not so profound. No, my man, this is double. From 2 to 4, you have doubled. You have doubled what? You have doubled the amount of CO2 released from the blood in the lung. In other words, you have doubled the amount of CO2 being kicked out of the hemoglobin. Go to hell. Now, when the hemoglobin has kicked the CO2 out, this doubles the pickup of CO2 in the tissue, because the tissue is now more likely to give the CO2 to the hemoglobin because the hemoglobin is empty. But this is not like actually double, it's almost double. Oxygen-induced hypercapnia has 3 main causes and 4 main consequences. I'll leave you to read them, so easy. Let's compare between the Bohr's effect and the Haldane effect. Definition: Bohr's effect, B, so start with a C. When CO2 binds to the hemoglobin, oxygen tends to leave. This is increased oxygen delivery to the tissue. What is the Haldane effect? When oxygen binds to the hemoglobin, CO2 tends to leave. This is called increased CO2 unloading or increased CO2 delivery. If you pay attention, Bohr's effect is nothing but shift to the right of the curve. What kind of curve? This is the oxygen dissociation curve. Haldane effect is also a right shift of a curve. What kind of curve is this? This is the CO2 dissociation curve. You have shifted the oxygen dissociation curve to the right, which means you increase oxygen delivery to the tissue, and you have shifted the CO2 dissociation curve to the right, you can say to the right and downwards, and you have increased CO2 delivery to the tissue. That's it. For more premium videos and courses, check out my website, medicosisperfectionalis.com.